All right. Yeah, so let's continue. Before I continue with the examples, is the pace okay of the class? Because I feel I might be going a little too fast, but this is kind of introductory stuff. So if it's going a little too fast, then just tell me. Okay, it will slow down when we get to other stuff. Okay. So we're going to do a few simple examples. All these examples and most of what I've done so far you can find in Nielsen and Chuang, so you can refer back to that book. Okay. So what we're going to talk about now is, so this is example 1. Let's call this Qubit Copying. Now, in a classical computer, okay, so in classical computation, do you know what operation clones a bit? So suppose I have an unknown bit, it's 0 or it's 1, and I want to copy it to a friend bit.
Fan out.
The?
Fan out.
The C0, exactly. So you just apply a C0 operation, okay? And this copies a bit. Okay, so you have your unknown bit, it is either 0 or 1, and you have your ancilla friend that you want to copy this value onto, okay? And then you apply a C0. So a C0 takes, it does control not. So this is 0, so that stays 0, 0. Okay. And here 1, which means you flip your ancilla, your friend qubit, then you end up with 1, 1. Okay, so what this operation did is it copied the value of bit 1. So it copied bit 1 into bit 2. Okay. Now what we're going to do is we're going to just look at simple exercise. What happens in the quantum case? Can we apply a C0 and try to copy a qubit? Okay. So what happens in the quantum case? Okay. And before I do the one-line math, maybe you can just vote yes or no. The yes/no question is, does it copy, yes or no? Okay, so pretty much everyone knows the answer. It does not copy. And let's see how this plays out and what happens. So we're going to start with some psi. Okay, this is the state that we want to copy. It's a qubit. So this psi is going to be some alpha 0 plus some beta 1. Okay. And we're going to have a friend qubit that we want to copy psi onto. Okay. So if we have psi and the reset qubit, okay, then the joint state of these is just alpha 0, 0 plus beta 1, 0. Okay. And now let's write a little algorithm that does a C0. So we have, this is psi here, psi. Okay. And this line over here, this symbolizes our new qubit. Okay. And what we're going to do is we're going to do a simple C0 operation. Okay, so this is a simple C0 operation. So we started off, so at this time point, we were in this state over here. Okay. And after the C0 operation, what happens? So alpha 0, 0 stays alpha 0, 0. So this is, so here, let's define this as psi initial. So this is psi initial. So here we had psi initial. Okay. And here, this is psi final. Okay? And so psi final is going to be alpha 0, 0 plus, now we have control naught, beta 1, 1. Okay? Now, as you can see, this is different than what we wanted. Okay? This is not the copying operation that we wanted. Okay? Let me write explicitly on this board here what we actually wanted. Okay? Remember, we wanted to copy the qubit. So we started with psi and 0. We applied the C naught, and what we wanted, if we had an operation that copies a qubit, we wanted to end up with psi. Okay, so this is what we wanted to do. But psi is just alpha squared 0, 0 plus alpha beta 0, 1 plus beta alpha 1, 0 plus beta squared 1, 1. Okay? So this is a state that can be separated into psi. And here, what we wrote on the other board, our result psi final that we got, okay, that was alpha 0, 0 plus beta 1, 1. So we got a non-separable state. Okay, we got an entangled state, which is non-separable, which is very different to this. Okay? Now, unless our initial state, okay, if psi I, if that was a classical bit, meaning it was just 0 or 1, then we would have had copying, right? Because having the classical bit be 0 or 1 amounts to having alpha being 0 or beta being 0. Okay, and if you put here alpha 0 or beta 0, then you have just copied it. Okay? So in the classical case, you have copied it. Okay? So this is a nice example where you do the same operation as classical and it doesn't work in the quantum case. And what we're not going to prove is something that some of you may have heard of, which is called the no cloning theorem. Which, as its name states, means you cannot clone. Okay, if you have an unknown state, okay, you start with some state which you don't know what it is, you don't know what alpha and beta are, and it can be a state on a bigger Hilbert space, it doesn't matter. You cannot take the state and copy it. Okay? There is no way you can do that. Okay? But we're not going to go through the proof. What we are going to do is we're going to look into another simple example called teleportation. Okay? Maybe I'll just start here. So, are there any questions about the qubit copying thing? No? Okay, trivial enough. Okay, so in this teleportation example, we're going to ask the simple question of, we have a state, okay, so we have state psi, and we want to send psi, which will be a qubit, from who to who? In quantum information, who do we? Alice and Bob. Thank you. All right. From Alice to Bob. Okay? So we want to send this qubit from Alice to Bob. What's the simplest way of doing that? I have a qubit. I have something here. I want to take it over there. What's the simplest way of doing it? Anyone?
Take it.
Just take it over there.
Yeah, just take it over there. Thank you. All right. Put in car and drive. Okay. Now, putting car in drive is fine, but it wastes gas, and some people get upset because there's global warming. So we don't suggest that. So we have to find a different way, okay? And the other way is teleportation. Okay, so we're going to do this example now. And note that when we mean teleportation, it means we want to take the state and we want to take it somewhere else now. As is, we don't know what the original state. Okay, Alice has the state psi. Okay, she doesn't know what it is, but she wants to give it to Bob. Okay, and she can't use the car because environmentalists are upset. Okay, all right. If she did know the state, by the way, what could she do without going into the car? If she knew alpha and beta, she could just pick up the phone, right? And just tell Bob, look, alpha equals this and that, and beta, and then Bob can just take a reset qubit and prepare that qubit on his side. Okay? So that's also a way of transforming that information, but Alice has to know what psi is. Now, why can't Alice just measure what psi is and then pick up the phone and send to Bob?
Because then the qubit would collapse.
Okay, but she measures, she knows the state, right? The problem is, remember I said, you can only get one bit of information about a single measurement. Okay? So if she has that state and she measures it one... Sorry? What was that?
Computation needs to know alpha to an infinite numbers.
Exactly. If she had many copies of psi, then she could measure each copy, okay? And then infer alpha and beta from that. Okay? She could do a thing called tomography. Okay? But she can't do tomography because she only has one copy, and no cloning says she can't copy it. Okay? If we could clone, she could copy it many, many times, measure all those psis, infer alpha and beta, pick up the phone, and tell Bob. Okay? All right. So she can't do that. By the way, a question, does everyone know what tomography is? Maybe answer just yes or no. I see 2 no's and no yeses. 2 yeses. All right, there are sufficient, okay, there are sufficient no's that, okay, so maybe I'll explain this. So on this board here, we're going to do an interlude to tomography. Maybe we do that first, and then we'll continue with our teleportation. Okay, so interlude to tomography. Okay, maybe this should have been like in the notes and done beforehand, but it's fine. Okay, so the way you do tomography, remember, you have some psi, okay, and psi is some alpha 0 plus beta 1. Okay, this is a state. This can also be a multi-qubit state, so you can have many, many qubits with many, many amplitudes. Okay, but the idea is that you have, every time, you have many, many copies. Okay, so if you want to do tomography, you need many copies. Okay. And each copy gives you some information. Okay, so, and you have to measure, the important thing here is to get the coherences, you have to measure not in a single basis. If you just measure in a single base, that doesn't help you. Okay, so for example, remember our block sphere over here. Okay, this is our block sphere. And if I only measure in the z bases, so I get answer of 0 and 1, okay, then measuring z will basically give me alpha squared right? And because I know that alpha squared plus beta squared equals 1, it will give me alpha squared and beta squared, okay? But that's all it can give me. It doesn't tell me anything about alpha itself or beta itself. Okay, for that, I would also need to measure in the x basis and in the y basis. Okay? And basically, if you measure z, you can infer from that the average of the operator z. Okay? And if you measure x, you can infer from that the average of the operator of x. Okay? And if you measure y, you can infer from that the average of y. So you do many, many statistics, right? You take this copy, you take a third of the copies and you measure z on them. You take a third of the copy and you measure y on them. Take a third of the copy and you measure x on them. And then all the x's you average down and you get average x. Same for y and same for z. And then you have x, y, and z. And these x, y, and z will just correspond to some coordinate on the surface of the block sphere, assuming it's a pure state. We'll get to non-pure states in a moment. But if it's a pure state, then you'll get some coordinate here on the sphere, which will be x average, y average, and z average. And from these three coordinates, you can infer basically theta and phi. And then from theta and phi, you can infer the complex values of alpha and beta. Okay? Now this can be generalized to a collection of qubits also. Okay? The important thing to notice is that one qubit, okay, one measurement gives us how much information? 1 bit. Okay? If we measure now 2 qubits, how much does each projection give us? 2 bits. Okay, good. If we have 4 qubits, from each measurement we get 4 bits of information. The big problem with tomography is that as you increase the number of qubits, your measurement increases linearly. So with each added qubit, you only get 1 more bit of information. But your information content goes, your Hilbert space grows exponentially.
Go to the end.
Okay? So, you know, your measurement goes like n, okay? But your Hilbert space goes like 2 to the power of n. Okay? So tomography can work for very small systems of qubits if you want to infer the state. Once you have many qubits, this becomes completely inefficient. Okay? And doing tomography for systems of 8 or 9 qubits is just practically impossible. Okay? All right. Any questions till now? Everybody understands what tomography means? All right. Mark yes or no if you understood tomography. All right, everyone's green. Excellent. Okay. So we want to continue with the teleportation. Okay. And we talked about the tomography, and we said that we want to teleport. So another thing about teleportation is that as opposed to having many copies and doing tomography on them, right? If Alice, let's say, had 10 copies, she could measure all those and pick up the phone to Bob and send it to him. And then Bob would have his psi up to the accuracy of the number of copies that Alice said. In teleportation, what you will see is that you get an exact copy on the other location. Okay? All right. So what I'm going to write now is basically the scheme itself. Okay? And then I'm going to do a couple of lines of math that show the teleportation itself. So let's write the scheme, the general idea behind the scheme, and then do the math behind it. Okay, so this is the scheme in words. Okay, so the first step that happens is that Alice and Bob they need to share a bell pair. Okay, so teleportation doesn't come for free. You can't just take a qubit and teleport it. A priori, there has to be a bell pair, and one qubit of this pair has to sit with Alice, and the other qubit from the pair has to sit with Bob. Okay? The second thing is that the second thing that happened is that Alice, she entangles psi with her qubit. Okay? Maybe I'll write qubit with her. Maybe not write qubit, bell qubit. Just to make it explicit. So she's going to entangle psi with her part of the bell pair. Okay, with her qubit from the bell pair. The third thing that will happen is Alice will measure. Okay, so she's going to measure her qubit and her bell pair of the qubit. So she's going to get 2 bits of information, one from her qubit and one from her bell pair. And then what will she do? She's going to, anyone? Pick up the phone.
Tell him the answer, the result.
She will pick up the phone. That's what I said. Okay? Yep. She's going to pick up the phone. Right? So Alice will measure and call Bob. Okay? And on the phone, she's going to tell him her 2 bits of information. Okay? And with those 2 bits of information, Bob will operate accordingly. Okay, so dependent upon the results that he hears on the phone, he will do some operations on his side of the bell pair, and then that qubit will arrive on his side, basically. Okay, completing the teleportation. Okay, so I'm going to move to the next board here, and I'm going to write explicitly the circuit. Okay, and then we're going to go step by step and see what happens to the wave function. Okay, so teleportation. So we start off with Alice. So we have Alice here. Okay, and Alice, she has psi. This is the qubit that she wants to send. Okay, so this is going to be the line representing the qubit that she wants to send. Now Alice also has her half of the bell pair. So this will be her half of the bell pair. And Bob is sitting far, far away. Okay. So this is Bob. And all Bob has is his part of the bell pair. Okay, so this here, this is the bell pair. So this is psi bell. Okay? Okay, so at the beginning, so let's mark this. This will be 0. Okay? So at 0 time, we're just going to have our initial state. Okay, so our initial state, psi 0, 0. This is just psi and psi bell, basically. Okay, which is 1 over square root of 2. alpha 0, okay, 0, 0 plus 1, 1. This is our Bell pair, plus beta 1, 0, 0 plus 1, 1. Okay, so this is completely separable. We have this thing and this thing. Okay, and what we're going to do now is we're going to do what's written on the board. Alice is going to entangle her qubit with her part of the Bell pair. Okay, so the way it's written down here is she's going to do a C0 operation. Okay, we saw before when we were doing the qubit copying example that when you do a C0, it basically entangles your qubits. Okay, so we're going to do this. So we'll call this 1. Okay, and so, oh, why did I put 2 zeros here? Just psi 0. Psi 1. Okay, so we're applying here a C0. Okay. And the result is going to be 1 over square root of 2. Alpha 0 and 0, 0 plus 1, 1 plus beta 1. But now beta is 1. Okay, and since we have 1, then these two are going to change. So 0, 0 is going to change into 1, 0. Okay, because this is our control. Okay, so this part is our control. And the target qubit is the first qubit of the 2 qubits in the Bell pair. Okay, so because this is 1, then this 0 is flipped to 1. Okay, and the same, we have 0, 1 over here like that. And this is our result after our C0. Okay? Now, what Alice is going to do is a local operation. She's going to do a Hadamard. The Hadamard is just for convenience. Okay? So we're going to write psi 2. So this is after the Hadamard. Okay, so we do a Hadamard here. Okay? And the Hadamard is applied to this qubit over here. Okay? So basically it takes 0 into, anyone?
1 over 2 squared, 0 plus 1.
0 plus 1, and it's going to take 1 into 0 minus 1. Okay? So let's write that explicitly. So now we're going to have 1 over 2. This is a half because when we're going to take this to 0 plus 1, we're going to get a square root of 2. Okay, so we take the square root of 2 out. And then we have alpha 0 plus 1, 0, 0 plus 1, 1, plus beta 0 minus 1, 1, 0 plus 0, 1. Okay? So, so this is psi 2 after the Hadamard. Okay? Now, the next step that's going to happen, now Alice is going to measure her qubit and her side of the Bell pair. Okay? So, let's, I'll erase this so I have more space. So now Alice is going to measure. Okay. And Alice is going to get one of 4 results. Okay. She can get 0, 0. So both qubit and bell pair give 0. Okay. If she does that, let's look at the y function. Let's suppose that she gets 0, 0. Okay. It means that this is 0. Okay. And this is 0. Okay. It means that we're left now with basically alpha 0 plus beta 1. Okay, so here, let's mark the measurement. So what Alice is going to do, she's going to do M1, measure qubit 1, and then she's going to measure qubit 2. Okay, so this is result M1 and result M2. Okay, and this is the results of M1 and M2, and this is 3. So measure, and I'm writing here the results from the measurement of psi 3. Okay, sorry. So if she measures 0, 0, then it means that psi 3 is just alpha 0 plus beta 1. Okay? So if Alice gets 0, 0, she just calls up Bob and says, well, you don't need to do anything. Okay? Basically, your side of the bell pair equals now the original psi. Okay? If she gets 0, 1, then psi 3 equals alpha 1 plus beta 0. In that case, she calls up Bob, and she tells Bob, okay, you need to do a NOT operation. Okay? Apply sigma x, and if Bob applies sigma x, so in that case, she would tell Bob, okay, Bob, you need to apply x. I'm sorry. My throat went dry. So she would tell Bob to do an x operation, and after this x operation, 0 goes to 1, 1 goes to 0, and Bob will have the original qubit. If the results are 1, 0, then psi 3 is going to equal alpha 0 minus beta 1. Okay. In that case, what is Alice going to tell Bob to do?
Apply Z.
Z.
A Z operation, right? So Alice will tell Bob to do a Z operation. And if the result is 1, 1, then psi 3 is going to be alpha 1 minus beta 0. Okay? And in this case, what Bob needs to do is an x operation followed by a z operation. So in general, we can write this as x to the power of, make the boxes bigger. So x to the power of m2, right? And this will be z to the power of m1. Okay? All right, because if 2 gives us a 1, then we want Bob to do an x operation. If 2 gives us a 0 and 1 gives us a 1, we want just a z operation. And if they're both 1, we want an x and then a z operation. And then Bob has his state. Now it's important to note that the state was not copied from Alice to Bob. Okay? Alice on her side now has 2 qubits that are reset. Okay? She knows the state of each of her qubits, and it is either 0 or 1. Okay? So the state psi is being destroyed in Alice's site, and it is being teleported to Bob's site. So there's no cloning here. Okay? There's no copying of the state. as soon as Alice performs the measurement, that measurement destroys the state at Alice's site and creates it at Bob's site. Okay? Are there any questions about this so far? We're following? Okay. All right, so the next example that I want to do is going to be Deutsch's algorithm. This is basically the simplest algorithm you can think of. It shows that it shows a simple operation that you would have to apply twice if you did not have qubits, if you only had bits, and that you can apply only once if you have 2 qubits. Okay. But before that, I want to give you the kind of like the general concept of what a quantum algorithm looks like. Okay, describe what a quantum computation looks like in general, and how to think about it. And then we'll do this Deutsche algorithm example. Okay, and after that we'll start talking about ensembles of qubits. Okay, density matrix and real measurements and so on. Okay? All right. So, a little interlude about, how to think about quantum computation versus classical computation. Okay, so let's call this quantum versus classical computation. Okay. And if we look at a classical computation, okay, we know that we have some n bits, okay, in this classical computation, and we know that each bit is, has a value. Each bit has a deterministic value of 0 or 1, right? 0 or 1. Okay. And then a large register of qubits would have some deterministic value, 0, 0, 0, or 0, 1, 0, 0, or whatever. And, there are 2 to the n numbers that you can represent with n bits. Okay? All right. And the way you do a computation is you take a register, let's say a register of 3 bits, okay? And you will input that register. Maybe I'll cut the board like this so I don't undo the quantum keys. Yeah, like that. Okay. And then you would put it into some processor that does some computation. It does some logical operations, C0, AND, NAND, whatever between these things. And at the output, you will also get 3 bits. And these 3 bits are going to be some function of your input bits. And this could be, for example, I don't know, like 0, 1, 1 or something. That's the answer. And if you want to calculate for input 0, 0, 1, then you would have to take this in, and you would get f of 0, 0, 1. Okay? And then you would have to repeat this for all the inputs that you want to do. Okay? And this is basically what you do in a regular computation. You take those 3 bits, you take this, and you repeat this through and through for all the inputs that you want to calculate. Okay? And you always get some function of this input. Okay? You can do the same with a quantum computer, just, instead of using the qubits, use the bits, and it's the same thing. But in the quantum case gives you something extra. Okay? So in the quantum case, we have n qubits. Okay? And these n qubits are in some linear combination, right? They're in a superposition or entanglement, right? So basically psi is some alpha 0, 0, 0, whatever, plus beta, I don't know, whatever, 0, 1, plus gamma, I don't know, whatever, 0, 1, 0, plus so on and so on. So I have a superposition with an amplitude to each of those 2 to the n states. And what you do in the quantum case is you take psi, right, and you put psi into your computation. Okay? And your computation are just unitary operations. Okay, so single qubit gates, 2 qubit gates, you can expand it into 3, 4, whatever, n qubit gates, but at the end you can decompose this into single and 2 qubit gates. Okay? So you have many unitary operations, and what these unitary operations do, they spew out at the end some psi prime. Right? So you have an input wave function, and at the end you have an output wave function. And this wave function will also be some alpha prime, 0, 0, whatever, plus beta prime, 0, 0, 1, 0, whatever, plus gamma prime, and so on and so on. Okay, so you input a wave function, which is superposition, and you have an output of the wave function, which is superposition. And what you do at this point is, what do we do at this point? We measure. Okay? So we measure. Okay? And then this measurement will give us, with probability, it will give us basically, 0, 0, whatever, with probability alpha prime squared, and will give us, the result 0, 0, 1, 0, whatever, with probability beta prime squared, and so on and so on. Okay? Now, from the other examples and the simple things that we saw, we can understand that what's happening here is that these amplitudes, a bit like you saw in the qubit copying or in the teleportation, it will be nicer in the Deutsche algorithm that we'll do in a moment, is that these amplitudes add up together, okay, due to the unitaries. If you remember the first example where I showed you 2 qubits, and I said alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1, and then I said, okay, suppose that alpha equals delta equals 0. And then suddenly those 2 qubits were entangled and we're in a Bell state. Okay? And that you can do with, like we saw in the teleportation, with a C0, for example. A C0 will create this Bell pair. Okay? So that's manipulating these amplitudes. Okay? And the way you can think of it in a qualitative way is an interference of these amplitudes. Okay? They add up and they can cancel each other. Okay? And what you want in a quantum computation is to manipulate, okay? You want to manipulate your wave function in such a way that the answer that you're looking for will come out with the highest probability. You don't know what the answer is in advance, okay? But you want to set it up that, you will have, let's say, these are all the results, you would have some kind of interference pattern, and your answer will have the highest probability if, this is probability. Okay? So you want to think about what's going on here as an interference, and what's happening in the measurement is now that you're sampling from this interference pattern. Okay? And so you want your answer to be highest probability. And what you can get out of this, as opposed to the classical case, is that you can get information which is collective information about your system. Okay, which you couldn't do in the classical case, because in the classical case, to get collective information, you have to repeat for all those cases and acquire information for each case. In the quantum case, you can take collective information, and then the hard part is to somehow interfere it to going into one result. Okay, so now let's be explicit about this and do Deutsche's algorithm. Okay, so this is basically the simplest example that we can show. Well, the simplest example that I know of that shows such a thing. Okay. Are there any questions so far? No? Okay. All right. So this is Deutsche's algorithm. Note that this is not the Deutsche algorithm. Deutsche is just slightly more expanded. So what I'm showing you is really the simplest case, the simplest thing there is. Okay? And the idea of this algorithm, what this algorithm wants to know, this is a 1-bit algorithm, or a function of 1 bit. So we have some f of x. So x is a 1-bit input, can be 0 or 1. And f will give us a result, 0 or 1. Okay? And what this algorithm is asking, it is basically asking, is f of 0, does f of 0, f of 0 equal f of 1, or does f of 0 not equal f of 1? Okay. Now, if f of 0 equals f of 1, it can either be 0, so it can be that f of 0 equals f of 1 equals 0, or f of 0 equals f of 1 equals 1, or f of 0 does not equal f of 1, and then f of 0 equals 0, and f of 1 equals 1, or f of 0 equals 1, and f of 1 equals 0. Assuming I did not permute anything, because that sentence was a bit confusing, I think that is it. Okay? So this is what this algorithm is going to do. Now, in the classical case, to figure out this algorithm, we would need to query f, okay, twice. We would need to run once with the input 0 and get f of 0. Then we would need to run another time with the input 1 and get f of 1. And then we can compare them and we can know, are we in this case or are we in this case? Okay? In the Deutsche algorithm, what we're going to show is that with one query of the function f, we're going to get our result. Okay? So this is the point of this thing. And the idea, and so what I'm going to do, I'm going to write the circuit for the algorithm, and then we'll go through it step by step. So, wait, what time is it? Oh, okay. We've got 3 more minutes, so I'm just going to write the circuit, and we'll go through it step by step next week. Okay? So, 0 and 0. So we start off with 2 qubits, okay, that are reset. Okay, and the algorithm goes like this. I'll write it down and then I'll go step by step and explain what's happening. X, H, then we apply a unitary. This is our calculation itself. So we have an input X and an input Y, and the output on this qubit is X, and here it's going to be Y plus f of X. Okay, and then you apply some Hadamard and do that. Okay, so this is the circuit. I'll just run through the circuit and then we'll do the calculation later. But what happens, you start with 0, 0. This is some unitary that encodes the answer to f. So depending on what f is, this will be a bunch of gates. Okay? So first, you start off with 0, 0. These operations are local operations that basically create some initial state that we want to start off with. It creates a superposition for this qubit, and here it creates a superposition with a minus sign for this qubit. Okay? And these go into here. And this is basically the operation itself. So on the output here we'll have x, and on the output here we'll have, sorry, this should be y plus with a circle, so it's y, bitwise addition f of x. Okay, so if y is 0 and f of x is 0, then the output here will be 0. If y is 0 and f of x is 1, then the output here will be 1, and so on and so on. Okay? So you can run all the combinations through this thing, and you'll get, your 2 bits out. If you start off with this, you can do this at home if you want. We'll do this at the beginning of next lesson. And you can figure out, and you can see that you will be able to get with one run of this thing, your answer is, does f of 0 equal f of 1? Okay? Which you can't do if you did not input superpositions into here. Okay? Basically classical bits. Any questions? Okay, so if there are no more further questions, we're done. If anyone has questions for after class or whatever, that's also okay. You can stay on the Zoom and ask me. I'm here another 3 minutes to answer questions.
Thank you very much.
Bye, thank you.
Thank you.